This penultimate section collects a handful of official SAT problems. The word penultimate, if you didn't know, just means next to last. We got one more section after this. Okay, official SAT problems, they were taken directly from SAT tests, or actually released SAT tests. SAT used to be Scholastic Aptitude Test, but now it stands for just SAT. Anyway, SAT is the test, college entrance exam that most of you are going to be taking before you leave high school. It's usually taken in the 12th grade. However, in the 10th grade and in the 11th grade, you take the PSAT. P in this case means pre or preliminary, PSAT. Okay. And again, it is indicating for colleges, are you prepared to do the level of work that we expect you to do in college? And a little secret is that after you pass the Algebra 1 STAR test, there's no more math STAR tests for you. There's not one for geometry, Algebra 2, or anything else. The only math tests that you have to worry about are any PSAT, SAT, or any AP tests that you choose to take. And we have AP Calculus, AP Statistics, and AP Computer Science are all categorized as the math classes. Okay, for those of you who do not know, the SAT is a college entrance exam that asks questions in an unconventional manner in the areas of reading, writing, and of course, mathematics. The modern SAT has two math sections, only one of which permits the use of a calculator. So you can use a calculator in one, and the other one, no, sorry, not even one of those kind of four function calculators. Nothing at all. You got to do it all by hand. Where applicable, your honors geometry, algebra 2, and pre-calculus teachers will endeavor to incorporate SAT style questions throughout the year. So here is a preview of them. Now, in the 8th grade, chances are you may have taken the PSAT 8, which is kind of a scaled down version of the PSAT that's offered at the 8th grade level. There's one at the 10th grade level, which some of you 10th graders will be taking this school year, and 9th graders you'll take it the following year. So we offer it to both the 10th graders and the 11th graders to give them some preparation for the actual exam. So let's look at a couple of these questions, and let me give you some pro tips to kind of steer you in the right direction. What is the solution to the equation? And then here's this equation that has some fractions in it, and has some parentheses and stuff. And the first thing that you want to do is identify what kind of equation it is. Is it quadratic? Is it linear? Is it a system of equations? What do you have? Well, when our leading, our highest power here on our y is 1, it's got to be a linear equation, which means the goal, of course, is to isolate the y. That sounds pretty easy, right? The only thing that makes this complicated is the fact that you have some fractions along with some grouping symbols. As we talked about, though, the fractions can be easily dealt with just multiplying both sides by something. But I would suggest before you do that, actually distribute the 3 through the parentheses here. And 3 times a half makes that 3 halves. Keep it as a fraction. Don't turn it into a decimal. Again, you're thinking of having to do this without a calculator, and it's actually easier to work with fractions than decimals without a calculator. Okay, and then plus 15y. And remember, our tip here is to multiply both sides of this equation by a number that's going to get rid of all the fractions. How do you decide what that number is? Well, you take a look at your two denominators there and get a common denominator, and that will tell you what to do. Now let's look at 79. In the system of equations below, a and b are constants. That means that these are not supposed to be variables here. The a and the b aren't supposed to be variables. They're hidden numbers, should be some sort of constant value. The s and the t, it's where the x and the y usually are, right? Those are the actual variables. If the system has infinitely many solutions, what is the value of a? Okay, so even though it has an A and a B, it's only asking for A. This would have been probably a multiple choice kind of question for you to choose between. And sometimes those multiple choice answers steer you in the right direction, help you out in some kind of degree, and you don't have access to those, of course. So there's one thing that I left out of the discussion about systems of equations, and that is infinitely many solutions. And I did it on purpose because we needed to talk about it right here on 79. So I'm going to go back to the systems of equations. And remember our systems of equations, well, that's quadratics. Where are systems? Right here. What your goal is to do is to find where your equations intersect each other, and that point of intersection is your solution. However, when you have two lines, sometimes that doesn't happen. So as far as possible solutions go with systems of equations, there's actually three possibilities. The first one, possibility one, that is when we have our graph, and then here's one line, and then here's another one of the lines, and they intersect at exactly one point, and then you have one solution. Okay, so there is case number one. Case number two, draw myself a graph, and then here's one line, and then here's another line, and these two lines are perfectly parallel to each other. In no kind of way can I find where these two things are going to intersect each other. This has zero solutions. Again, you have zero solutions when your two lines are parallel to each other, and I know that they're going to be parallel when they have the same slope. One last possibility. That is, I have my two lines that I try to graph. What a wiggledy y-axis. Anyway, so I go to graph my first line, and then I go to graph my second line, and the strange thing happens is that it lays right on top of the other one. I didn't realize it whenever I had my two equations, but one of them was a multiple of the other one, and in that case, I have infinitely many solutions. All the solutions that work with one equation work with the other equation. In other words, they also intersect an infinite number of times. So this is the case that we're talking about here. And something's getting on my nerves. It's not quite centered here. Okay, that looks a little bit better. Okay, so this is the kind of thing that we are trying to look for. And I'll give you an example of when this can happen. Let's say I have x minus 3y is equal to 4. If I take my equation and I multiply everything by 2, I get a 2x minus 6y is equal to 8. These two equations look different, but they represent the exact same line. This one lays right on top of this one. The second one lays right on top of the first one, so they would intersect everywhere an infinite number of times. That's the kind of thing that you're doing on question number 79. You have to basically figure out what do you have to multiply these equations by in order to make the coefficients match up. Now, when you look at it, the hint here is the fact that you only know the coefficients of S. Like you don't know the coefficients of T because one's a -2 and the other one's a B. So you can't really make those things match up. And you can't make the constant terms match up because, again, your A is some unknown number and then you have a -7. But I bet you can multiply something here to make the -3 and the -15 match up. And that's what your goal is to try to do, and then ultimately figure out what the A value is. Let's look at number 80. A voter registration drive was held in town Y. Okay. The number of voters V registered T days after the drive began can be estimated by the equation V is equal to 3,450 plus 65T. What is the best interpretation of the number 65 in this equation? So all this is asking you to do is interpret what this number is supposed to be in this real life kind of situation. This is a linear equation, and the 65 in front of the variable, it would sort of be like this. Y is equal to mx plus b. It's the same thing as this. That's what the 65 is. It's a slope. And usually when we write slope, writing with a highlighter, usually when we write slope, it's a change in y over a change in x. But we don't have y's and x's, so let's rewrite this with the letters that we actually do have. And our y value is the thing that is the dependent variable, which is the v in this case. So it's going to be a change in v over a change in x. And x is the independent variable, which is t, change in t. And now think about what the units are. The units are what's really going to help you figure out what this interpretation is supposed to be. Well, what does the v represent? V is the number of voters. So this is voters on top. And T is days, days after the drive began. So this is over days. So in other words, my slope should be, it is a rate of change, and this rate of change is measuring voters per day. And that's how I would suggest that you try to tackle this, distinguishing between these little answer choices that are here. Okay, over here on 81, if 1/2 x plus 1/3 y is equal to 4, what's the value of 3x plus 2y? Notice that they didn't ask you what x is. You can't find what x is because there's an infinite number of values of x that would satisfy this. If you ever wanted to know what they were, all you'd have to do is graph this, and then any point that's on that line would satisfy this equation. So that's not what it's asking. Instead, it's asking for an expression 3x plus 2y is equal to some number. It should be some sort of number. And your tip here is to try to make this right here, this 1/2 x plus 1/3 y, look like 3x plus 2y. And you could probably do that through some sort of clever multiplication, because if you multiply both of these sides by a certain number, it's also going to increase or possibly decrease this number 4 on that side, and that's going to tell you what this thing is going to be equal to. Okay, 82. What is the sum of the solutions? Sum of solutions of, and then we have this kind of equation. What kind of equation is it? Notice that we have a squared in here. If we were to FOIL this thing out here, this 2x, it's going to be squared. It's going to be a quadratic equation. Quadratic equations have two answers, and this is asking you to add up those two answers. Okay, so when we solve quadratic equations, remember that what we usually do is make the thing equal to 0 and factor. So here's a couple of suggestions for you. So I can definitely see it's not equal to 0, so I could take this guy and just subtract that whole entire term over to the other side as a 2x plus 1 squared minus x plus 2 squared is equal to 0. Now, at this point, you have two options. First option is to understand that this is actually a factoring pattern called the difference of two squares. This is a difference because there's a minus sign, and this is a square, and this is a square. If you recognize this as the difference of two squares, super easy to factor this thing. Let me show you what a difference of two squares looks like, actually. Let's say that I have x plus 5 times x minus 5. If I were to expand this thing out, I'm supposed to FOIL my first terms, x squared. X times negative 5 is the outside terms, is a negative 5x. My inside terms, 5 times x is a positive 5x. And my last terms, 5 times negative 5 is negative 25. And notice what happens is that the middle terms cancel, and I'm left with x squared minus 25, which is called the difference of two squares. Because x squared is a perfect square, obviously, and then 25 also is a perfect square. And it factors just like this. Take the square root of the first one, x. Take the square root of the second one, 25. Square root of 25 is 5. Put one positive and put one negative. So here's another little example for you. Let's say that I had something like 49 minus 36x squared. Both of these things are perfect squares, and I'm taking the difference between them. So I take the square root of 49, which is 7, Take the square root of 36x squared, which is 6x. Make this one negative and make the other one positive. Doesn't matter which one's which. Totally interchangeable. So you can apply that kind of principle, that technique right here on question 82. A lot more complicated though, because you don't just have a single kind of number here. You have expressions as things being squared. The alternative here is to expand each one of these things out by multiplying them by themselves, combining your like terms, getting a quadratic equation that you solve by factoring our quadratic formula. I would suggest factoring, especially since we're pretending like we're not using a calculator here. Now, a pro tip, whenever you go to expand this out, let me bring this right down here. 2x plus 1, when you square it, this is not equal to 2x squared plus 1 squared. That doesn't work. What does the squared mean to do? It means to multiply times itself. 2x plus 1 times 2x plus 1. When we have a 2 that's an exponent, that's not the distributive property. You do not distribute to that, to each one of the things inside of the parentheses. There's no such property that says that. If the 2 is out front, sure, you can do that. But when it's an exponent, you can't. It tells you how many copies of that thing you're supposed to multiply together as factors, and then you'd have to FOIL this thing. Whenever you're done, if you were to try to use this wrong technique, you're going to get no middle term here. But whenever you FOIL this thing out, you will get a middle term. So keep that in mind whenever you're expanding this out, if that's the method that you choose over here on 82. And then finally, last SAT kind of question, 83, scientists estimate that the Pacific Plate, one of Earth's tectonic plates, has moved about 1,060 kilometers in the past 10.3 million years. What was the average speed of the Pacific Plate during that time in centimeters per year? So speed is equal to a distance over the time that it took you to go that distance over time. And we're given both of these things. We're given a distance of 1,060 kilometers, and make sure that you put the units with it, over a number of years, which is 10.3 million years. So million is 10 to the 6. So I'm going to basically almost make this scientific notation. It's not technically scientific notation because this is bigger than 10. Anyway, and then this is years on the bottom. And in another video, previous video, I don't remember which one it was, which one of the weeks you were supposed to do this, is unit conversion. You just turn this into some train tracks here and start doing your little unit conversions. We want year, so nothing's going to change down here. It's the kilometers which have to change. Okay, so I need to turn kilometers into centimeters. Most people don't go straight from kilometers to centimeters. Usually you go kilometers to meters to centimeters. That's the easier way to go, even though it takes a couple of extra steps. So a conversion factor that you would need is that, well, kilo means 1,000, so there's 1,000 meters in 1 kilometer. 1,000 meters equals 1 kilometer. And I just have to figure out how to arrange my conversion factor. So remember, when you're doing this train track method, to organize your conversion factors, you want the kilometers to disappear by division. Our kilometers are on top, so that means my kilometers have to end up on the bottom, so 1 kilometer. And whatever it's equal to on the top is 1,000 meters, because essentially, even though it doesn't look like it, we're multiplying this quantity by a fancy 1, so it doesn't change how big or small it is. However, what it does do is get rid of those units. And then you'll have to do it one more time in order to get rid of your meters to turn this into centimeters in order to figure out what this thing is. And can you do this without a calculator? Perhaps. See what you come up with.